Okay, hello statics, tan 210, 211. So this is going to be an example of a frames problem that we didn't do, at least in my section. This is Professor Kirsch. So let's get right to it. So here we have a frame supporting some external loads in a moment as shown. So we've got the 400 newtons here and an 800 Newton meter external moment applied at this little point on the corner. And the question asks us to find the horizontal and vertical components of the forces on member BC at C and the magnitude of the reactions at B. So we're looking for the reactions at B right here and just its magnitude, and we want to know the horizontal and vertical components of the reactions at C, basically. So what's the approach to this problem? First, so what I encourage you to do is stop the video now, or when I say now, and think about how you're going to set this up. And then use this video as a way of checking if you're going along the right track, right? So rather than having a full written out solution, use these videos to try and kind of check your progress as you're going. Ideally, work the whole problem and then use the video to find and help troubleshoot if you can't find then an error. So the approach we're going to use here is to create free body diagrams, right? That's pretty much the approach we use every time. Free body diagrams of member BC. So recognize that this is all one object here. So let me erase. But pay attention, right? From C to B, this is all one connected object, so that's one member. And when we look at these frames problems, so recognize that this is not a truss necessarily, this is a frame. So you should be thinking about which free body diagrams are you going to need. You should check for two force members. And then at the end, once you've isolated the right free body diagrams, apply your equations of equilibrium. Okay, so since this question asks for things at B and C, let's go ahead and do a free body diagram of that member. So this is FBD of member BC, right? We'll create our standard coordinate system, X and Y. We don't have any thicknesses we need to worry about, so I'm just going to draw a free body diagram as these simple line members and then apply our external forces and moments. So at C, we're pin connected. We should have a CY and a CX. We have the 400 newtons coming down. We have the 800 Newton meter applied at that corner. And what do we know about B? So we can see here now we're checking for our two force members. So BC is for sure not a two force member, way more than two sets of forces. And there's a moment applied, so that automatically eliminates it as a two force member. Two force members are always members that are pin connected and only have forces acting at the pins themselves. But in this case, we do have one member that is a two force member, and that's member BA. And so what does that mean? That means that we're going to automatically know the direction of the line of action of the forces acting at B. So we can go ahead and include that. Whoops, I should say B. And if we assume BA is in tension, so we could do a free body diagram really quickly of member BA. The way I think of it is that we can assume this one is like this. So if this is B and A, then that means the reaction force here is going to be like this. In this case, for this problem, this doesn't really matter because it's just asking for the magnitude. So whether or not you get these signs, arrows pointing in the right or wrong direction, you'll still be able to get the right answer because we're just asked for the magnitude of the reaction at B. So here, this is going to be our unknown force, BA. Okay, so we have three unknowns, CY, CX, FBA. Three unknowns. Hopefully we can solve, right? This is statically determinate. So I guess the best thing now is to proceed efficiently. Think about what are you going to do to solve for these unknowns as quickly as possible, right? For a test or a quiz, that's definitely one of the constraints you have. So what we can do first, hopefully everybody sees we've got enough geometry such that what? Think about it for a second. We can take the sum of moments at C, right? positive counterclockwise. And that moment equation is going to be, so here we're going to take the moment right here. Cy and Cx will not be in our equation, but we'll be able to get FBA. We have all the geometry we need to calculate this moment. So the 400 newtons is going to contribute a positive moment times its moment arm, 2 meters. We have the 800 applied already. And now we have the two components of FBA. So we have geometry in the problem here. This is 1. This distance I'm drawing on the left-hand side of the screen is 3 meters. And now we can think about this angle theta. I tend to solve things in terms of angles rather than, so we can also do this way, theta, this is a triangle 1 and 3 here, right? So tangent of theta is equal to 3 over 1. Theta then is equal to 71.6 degrees. This is what needs to go into MATLAB, right? So MATLAB, solve. Don't put this in, actually put into MATLAB the atan value for 3 and then save that as a variable. You're going to need that later, and that'll help avoid any of the rounding errors. All right, so let me move my moment equation down here. Oops. So this was the 3. All right, so now we know what that theta is, right? So the x component of this is going to be the FBA sine theta of FBA. That's going to be a positive, and then times its moment arm, right? So this is the x component up here. And its moment arm is this distance here. So I think we always drew those in blue. And that's the 1 meter. So that's 1 meter here. Plus, what else? The y component of the FBA, force and member BA. So that's the cosine theta times the moment arm going from B to C, right? And that's the 3 meters equals 0. So the only unknown in this equation is FBA. I would go ahead and simplify this by hand. So we can write FBA cosine theta times the 3 meters plus FBA sine theta times the 1 meter. We know it's going to be equal to the 800 plus 800 taken to the other side, minus 1600 Newton meters. Pull out FBA, 3 meters cosine theta plus 1 meter sine theta equal minus 1600 Newton meters. So now, take this part, solve this in MATLAB. Okay? And save it as some variable. Right? Let's save that as some variable A. And so then what you're going to do is solve for FBA is equal to minus 1600 Newton meters divided by A. And that is, again, another MATLAB variable that then you can put in right away into Prairie Learn. So there's one, right? And so, of course, we want the absolute value of this, so whatever A is. If this is still a negative, the question asks us for the magnitude of the reaction, so we'll go ahead and put that absolute value. Okay, so that's one part. So now let's go back and find the reactions at C. I'm going to recopy this free body diagram just so we have it handy in our screen. Let's solve for this. Okay, so if you're at this point, pause the video and go ahead and think about how you're going to solve for Cx and Cy, and then come back and check if you get the right answers. Okay, so hopefully you're done. It's like a cooking show. Now we can take, how are we going to solve for this? It's only 2 more unknowns. We already have FBA. We're going to do sum of forces X, FBA, sine theta, plus CX equals 0. So whatever the value is for FBA that we got up top, whether or not it was positive or negative, you're going to carry that through down at the bottom, right? So CX is equal to minus FBA sine theta, and that should give you 800 newtons. And now sum of forces Y. We have CY going up, minus the 400 coming down, minus FBA cosine theta equals 0. And so then you should solve for CY equal 133 newtons. Now those two are positive numbers, our directions are correct, so you'll go ahead and continue with putting the positive numbers into Prairie Lar. Okay, and that's how you solve that problem.